Let's take some more interesting functions and start to look at their Maclaurin and Taylor polynomials. I want to find a fourth degree Maclaurin polynomial for x squared e to the negative x. And then I want to kind of approximate f of 1/10. Now I'm not going to plug this into a calculator, but I'm going to show you how you would get there, what I'll call a calculator ready form. So to do this, we do it the same way we've been doing all the other ones. You have to find the derivatives up to the degree of interest. So we're doing fourth degree Maclaurin polynomials, so we need to find up to the fourth derivative. So we take our zeroth derivative function, well that's x squared e to the negative x. We take our first derivative of the function, that's going to be 2x e to the negative x minus x squared e to the negative x. Now what I'm going to do here is I'm actually going to combine this into a single term to make my life a little easier. So that's going to be e to the negative x times 2x minus x squared. And then when I take the second derivative, I get negative e to the x, 2x minus x squared, plus e to the negative x, 2 minus 2x. So then I can combine this again to say, I pull e to the x out here, e to the negative x I mean, and so then what I'm left with is a positive x squared minus 4x plus 2. I take the third derivative. I get negative e to the negative x, x squared minus 4x plus 2, plus e to the negative x, 2x minus 4, which gives me e to the negative x. So then I have a negative x squared here, plus 4x plus 2x, so plus 6x, minus 2 minus 4 minus 6. And then finally, I take the fourth derivative here. I get negative e to the negative x, negative x squared plus 6x minus 6, plus e to the negative x, negative 2x plus 6, which then gives me e to the negative x. So positive x squared minus 6 minus 2 minus 8x plus 6 plus 12. Okay, so that's kind of ugly here, but what's nice about this is that this is a Maclaurin series, so our center is 0. So when we take and e to the 0 is just 1. So anywhere you're going to see an e in these, it's just going to evaporate. It's just going to become a 1. And anywhere you see an x, it's going to be a 0. So your original function value is 0. Even your derivative is 0. Your second derivative, however, is 2. Your third derivative is negative 6. And your fourth derivative is positive 12. Because, again, these disappear, all those disappear, and then this is just a 1 on the front end. So you're really only left with those extra terms. So what we really only have are these three terms here. Polynomial is our leading term over 0 factorial x to the 0 plus 0 over 1 factorial x to the 1 plus 2 over 2 factorial x squared. So again, we're just walking up. We're just walking up from k equals 0 to up to n, from k equals 0 up to n. Negative 6, 3 factorial x cubed plus 12 over 4 factorial x to the 4th. So at this point then we say this is going to disappear, that's going to disappear. That's just going to become x squared minus x cubed plus 1/2 x to the 4th. So at this point what you want to do, if you want to approximate f of 1/10, you would just do p of 1/10. So that's going to be 1/10 squared minus 1/10 cubed plus 1/2 1/10 to the 4th. Now this I can actually do. I don't have to approximate this. This is going to be 1 over 100 minus 1 over 1,000 plus 1 over 20,000. So this is my common denominator of 20,000. So I get 200 minus 20 plus 1 over 20,000, which then becomes 181 over 20,000. So you'd have to, that you would want to plug into your calculator, or you could just, well, we can do it. We can say that's 905 over that, so that's 0.00905. Is that seems correct? It's kind of a lazy man's way to do that. So I don't actually know what the value of f of 1/10 is, but I would bet it's pretty close to that. Worth a plug-in. So that's the idea. Once you get the polynomial, you can use that polynomial to evaluate or approximate the function values there. Now over here, what we want is a second degree polynomial, but it's a Taylor polynomial with the center not at 0. So we have to be a little more careful. But the process is really the same. So I have to get the 0th derivative, which is x squared sine x over 2. It's just the function. Then I have to get the first derivative, which is 2x sine of x over 2 plus x squared cosine of x over 2 times 1/2. Right? That's the product, or that's the product rule in action. And then I could probably clean this up, but I'm not going to, just because we only have one more derivative to go. So I'm going to get 2 sine x over 2 plus 2x cosine x over 2 times 1/2 plus 2x cosine x over 2 times 1/2 plus x squared negative sine x over 2 times 1/2 times 1/2. Now, I skipped a lot there. I hope that you understand the product rule well enough that that's not super confusing for you. If you don't, please refer to previous videos or other videos about the product rule. Again, that's kind of ugly, but it's gonna clean up a lot more than you think when we actually plug in our value at our center here. So I'm not gonna do it to the side here because there's not that much room. So at pi, I get pi squared sine pi over 2. So I can just get pi squared. At pi for the first derivative, I get 2 pi sine pi over 2 plus pi squared cosine of pi over 2. So times 1/2. Right, so this goes away. Cosine of pi over 2 is 0. And sine of pi over 2 is 1, so I get 2 pi. And then for the second derivative at pi, so what you notice is if every time at the cosine it disappears, I don't even have to consider those. So I'm just going to throw those away. So I end up with 2 sine pi over 2 plus pi squared negative sine pi over 2. It's 1/2. So again, sine of pi over 2 is 1, so that's 2. And then that's a negative 1. So that's going to be 2 minus pi squared over 4. So now that we have that, we can make the approximating polynomial. So it is pi squared over 0 factorial x minus pi to the 0 plus 2 pi or 1 factorial x minus pi to the 1 plus 2 minus pi squared over 4 over 2 factorial x minus pi squared. So you just keep, again, you're just following this process. You're doing x minus the center to the power, and then you have the factorial of the same, I guess not degree, but like the same number there. And then the only thing that's different are these little terms here, which come directly from that. So then we end up with pi squared plus 2 pi times x minus pi plus, I'm going to say 1 plus pi squared over 8, or minus pi squared over 8, x minus pi squared. Right, because this is 2, so 2 divided by 2 is 1, pi squared over 4 divided by 2 is pi squared over 8. So what you see here is you have pi squared is kind of your center point. It is, or it's your anchor point. And then you have a linear function here. This is just a line shifted over by pi and then scaled by 2 pi, so it's relatively steep. And then you have this. Now, this is shifted over by pi, but 1 minus pi squared over 8 is probably pretty small. Pi squared is like roughly 10. So this is, 1 minus 10/8, so like 1 minus pi 4, so it's like negative 1/4. So it's really not nearly as steep as these. So this doesn't start to dominate until later, which kind of makes sense because x squared near pi, or near that point, it's going to be pretty, at pi, it's going to be pretty close to what x squared would be normally. But that sign's going to have that wave function, so long term you want it to be dominated by this x squared, but in the short term you don't. In the short term it's going to behave much more like a linear function. So this kind of agrees with what you would expect for an approximation of that function.